All right, let's start the last session of the day. And the first speaker today is Erwan Alice. He's going to talk about the scattering transforms. Go ahead.
Thank you very much. So I hope you still have a bit of energy at the end of the day. So I will talk about scattering transform and their application to the separation of ISM phases, and I will show several examples. And okay, I apologize in advance. I will try to be clear on both for the astrophysics person and the data science person. So probably they won't, I will basically go and explain the main ideas without entering into the dirty details. If you want to discuss them, I'm extremely happy to, so don't hesitate to come and discuss, but I will mostly show the ideas during this talk. And also something that that is important is that during this talk, I will mostly focus on spatial structures and not on the spectral dimension. But that's clearly something that we want to include afterward. But when I give some general ideas, it's mostly about the spatial structure of the ISM. Okay. So in ISM studies, we have a big challenge, which is that we usually have a limited amount of intricate observations, meaning that, okay, we have a unique, mostly with respect to the typical time of a ground, static multi-frequency sky. In particular, if you look at degrees structures on the sky, you won't have a lot of sample. And usually we have a mixture of inhomogeneous components, so it can be difficult to have isolated processes, and in a lot of cases you need to do component separation. And that will be one of the main topics of my talk. And the difficulty when you do component separation is that in the era of machine learning, if you have a very, very nice model, there are super cool way to efficiently perform component separation and inverse problem. But you need to have a model, a very good realistic model. And at least for what concerns the spatial structures of the ISM, we don't really have a complete model. Numerical simulation or physical models are not necessarily done in order to have a 1% precision on the structures that we see on the sky. It's also a lot in order to understand the effect of the different dynamical contributions. And even if you have very good simulations, they are very expensive. So in a lot of cases, and I would say in most cases, we don't have like extremely good prior model on which you could train your neural network, it makes component separation particularly challenging. And so the idea that I want to discuss during my talk is, okay, still can we do this kind of component separation directly from observational data and without relying on external model? And to give a bit of flesh on this question, I will give two examples that I will study during my talk. So the first, it's more an application on CMB studies, but here what you have is a 20 by 20 degrees observation of the polarized sky at 353 gigahertz, so CMB frequencies. And what you see is a big structure here from the galactic, from the Milky Way, from the galactic emission. And you have a lot of noise and CMB. And here we are in a case where, okay, we have a good idea of what the noise here and the CMB here is. Here you have a sample of the contamination. We have a model. And actually, we can also look in total intensity. And we have a good idea of what the signal is because we have a much better observation. But the link between total intensity and polarized emission is very complicated. It's not a one-to-one correlation. It's very difficult to use. And here, the question that we can ask ourselves, and for cosmic microwave background, it's very important, is at which point can we have here a good reconstruction of the polarized emission from T's image and T's knowledge? And here you see that we are in a regime where, okay, we don't have a lot of data, basically only this square patch, and no one can give us a good model of the polarized emission. And a second application, more on ASM phases, is that, okay, here we look at a lot of radio observation of the interstellar medium, 21 centimeter radio observation, so H1. And there are several phases in the ISM. So there is the warm, which is more diffuse, and the cold, which is more dense, neutral media. And these are phases that we know have different spatial properties. Okay, they also have different spectral properties. We let that aside for the moment to see what we can do only from the spatial properties. And we have, okay, well, from these observations that I will use, we have only a few thousand of unlabeled mixture of WNM, CNM, and noise. So can we, only from this observation, not relying on any external model, learn a model and separate these phases directly from the data? And here we are in intermediate data regime. We could maybe use some kind of unsupervised approach, but we also lack prior models. And the questions are, how can we try to solve these difficult problems? So that's case studies that I introduced in order to explain the kind of things that we can do with new tools, which are the scattering transforms. So to try to answer to this question, so there is a path which is through scattering transform, which are new, recently introduced statistics that allow to construct generative model of physical fields, and I will show how it works. So, okay, scattering transforms have been introduced 15 years ago now, something like that. And they have been initially developed in data science to try to understand why the neural network were so good at characterizing structures in images, and at which point we could inspire from them in order to construct summary statistics, like the power spectrum that you can write explicitly, but that will be extremely good at characterizing complex structures, okay? And so it led to a set of statistics, the scattering transform, which are extremely efficient to characterize structure, non-Gaussian processes, and still have low variance. And as I say to you, there are summary statistics, so scattering transforms, it's not machine learning at the moment. There is an explicit way, an explicit mathematical form for them, and you give me one image, I can compute the scattering transform in the same way I can compute the power spectrum, okay? And how they rely, how they are computed, it's basically you use wavelet filters to separate the different scale of a process, okay? And then you characterize the interaction between the different scales with nonlinearities. So here, I can give a small example. Okay, so sorry for the people who saw this slide already a lot of times, but okay, you have an observation. Here it's an inertial observation at 350 micron of the dust. It's 2 by 2 degrees on the sky. And what you can do is that you can perform convolution of this initial image with different wavelets, okay? If you don't know anything about wavelets, it's not a problem. Wavelets are just band pass, okay, filters. And you do a convolution, it's just linear filtering, okay? So you filter the initial image at different spatial frequencies, okay? Here you have basically, let's say, 8 pixel vertical oscillation, and here 16 pixel vertical oscillation. And as the wavelets are complex, you have the amplitude, the complex amplitude, which is the local amplitude of the oscillation. And you have the phase, okay, which oscillates here at 8 pixel vertical, 16 pixel vertical, but where you see also traces, okay, of the structures in the initial image. And actually, when you see structures, usually you have interaction between scales related to nonlinear processes in the image. And you can see it very well because here you see that the amplitude, the big structure here, you can see it very well in the way these amplitude at different scales are correlated. And you have same kind of things for the phase alignment. You can see very well for the structure here, okay? But even the diagonal filament, which is very difficult to see here in amplitude, you see it extremely well in phase, okay? And so what you can try to do is to characterize, estimate this interaction between the different scales, the statistical dependency, to get statistical features of the initial image. But actually, if you just want to compute a correlation, a covariance, we'll have 0 because they oscillate at different frequencies, and it's like computing the cos, the integration of cos x times cos 2x. It's 0. It's a perfect example of signals which are statistically dependent, but linearly decorrelated. So an efficient way, you can use high order statistics if you want to estimate this kind of information, but you will have a lot of term, a lot of variance. Rather, what you can do is inspire yourself from neural network and use nonlinearities. For instance, the phase harmonics, you keep the same amplitude, but you accelerate the phase by 2, and you have something that oscillate at 8 pixel vertical. But you see that if you compute a covariance, you will have something which is positive if the phases are statistically aligned, negative if they are statistically anti-aligned, and 0 if they are independent. And you can do the same also, for instance, with modulus. You remove the phase, you compute the covariance, and you have an information about the correlation between the local amplitude of oscillation at different scales. Okay, that's the broad concept beyond the scattering transform. I don't want to enter into the details, but each of these covariances, it gives you one complex number, and you compute the interaction between different pairs or even triplet of scale, and you have a vector of numbers which characterize this information, and it's your vector of statistics. Okay? So there is a family of statistics. They have different names, and they have been introduced in different years. You have the wavelet scattering transform, wavelet phase harmonic, wavelet scattering covariances, spectra. to be fair, you don't care. Let's call them scattering transform. It's much simpler. So I will speak about scattering transform. And if you want to enter into more details, we can advise you to use one or the other of the summary statistics, but let's call them scattering transform. And they have been used for a lot of characterization and parameter inference. I won't enter into the details. They have been shown very informative in for a lot of different applications, sometimes on par with convolutional neural network. And the only thing that I want to say is that what has been extremely impressive is that some statistics, some scattering transform statistics, which have been introduced, for instance, for interstellar medium, have been applied to weak lensing for images that look completely different, and still we're able to get state of the art without any modification, any tuning, which is a strong demonstration of the fact that these statistics are quite agnostic of the kind of process you try to model. And indeed, it's quite general, the kind of information that you get. It's just the interaction between different band passes in your process, okay? But scattering transform allows to do something which goes much beyond parameter inference and classification. They can be used to construct generative model of processes, okay? So what does it mean? Let's say you have a given map, a given image, S, okay? You can compute the scattering transform statistics. From now on, I will call them phi of S. And from that, you can construct a generative model of the process. So in a mathematical framework, what does it mean? It means that you assume that your initial map is sampled from a distribution that you will try to approximate, okay? So you have the distribution, you have one sample, you estimate the statistics from this sample, and you can construct this generative model from which you can sample additional maps. And this is done in a proper information theory framework. This is a maximum entropy distribution, which is the most general model that you can construct under the information you put into the model, which is the scattering statistics. And from a numerical point of view, the implementation is quite straightforward. If you put yourself in a microcanonical setup, I won't go into the details, but okay, you have your constraint, and if you want to generate a new map, you sample a white noise and you do a gradient descent in pixel space such that you reach at the end of the optimization a new map which has the same statistics than the initial map, and this is your sample, okay? So this has been applied to a lot of different processes. Here you have the kind of samples that we can generate from one single image. So the top row, okay, are realization from different processes. Here it's weak lensing, you have large-scale structure of the universe. Here you have two kinds of turbulences, one which is inhomogeneous, anisotropic, sorry, the other not. Here you have something. And you see that we were able to construct samples which already visually looks quite realistic with respect to the first one. They are not deterministic, just they are able to reproduce the typical structures. And if you look at the summary statistics, I mean, they are very well reproduced, power spectrum, histogram, bispectrum, Minkowski functional, I mean, up to a few percent usually, but keeping in mind that these statistics vary over several order of magnitudes, okay? And what is very good is that this model, so here that the same model that has been used to construct all these different processes, I mean, just with different summary statistics, and this model can be written with only a few hundreds of coefficients. So it's a very low dimensional model. And there has been various expansions, spherical, multi-channel, heterogeneous. I won't enter into the details. The only thing that I will say is that recently there have been development to spectroscopic data, PPV. Here it's an application of cosmology on the epoch of ionization, but I mean, conceptually that's the same kind of data as spectroscopic survey. And to give you an idea, here to the left, okay, you have a spectroscopic cube. X, Y are the spatial dimension. Z is the spectral dimension. So you see you have clearly a different structure on the spatial direction and the spectral direction. And here that's one target field, and that's the kind of realization that we can sample from one single data cube. And okay, there is still work to do, but it shows that the applications that I will show later on could be extended to a spectroscopic data cube. So now, before to go to the application to component separation, there is something which is extremely important and that I want to emphasize is that at the moment I showed that, okay, if you have one given sample, okay, you can construct a model. So you have the distribution you try to approximate, you sample a map, you estimate statistics, and you construct your generative model. But actually, you can, if you want, cut the first leg of this hierarchical relation. And and you can sample directly from the scattering space. So you give me a set of scattering statistics, and from this set of scattering statistics, I have a model, and I can generate different realizations. Which means, if you want, that I have a generative model of physical fields. And what I can do is I can vary the statistics, and when I vary the statistics, I will see the map that I sampled that will vary a bit in terms of properties. And in addition, I can have an idea of what these statistics mean. I can vary, for instance, I can go toward a Gaussian field. I can augment the filamentary structure. I can completely reduce to zero the filamentary structure. I will only see spherical structures. I can play a bit with it, okay? And it means that I have a generic low-dimensional parametric model of physical fields that can act as a prior model when no such model exists. And that's exactly what I will show. So we arrive to component separation, and I come back to this first example that I presented. So, okay, here, so polarized emission, we have the galactic emission plus a contamination that I know statistically, which is noise and CMB. And okay, it's a component separation. You can even here write it in an inverse problem setting. Okay, not completely, but I will put myself in this framework, which is that the data here are a forward model of the signal of interest, and the forward model is just to add a contamination, okay? And here I want to try to solve this inverse problem while having no prior model for S. But I can follow the scattering way, which is that, okay, I will assume that my signal is well described by a scattering transform generative model, which is parameterized by mu S, which is a vector of statistic of dimension a few hundred that parameterize the generative model. Okay. My data space is just, okay, here you have the data flow. You start from the parameters of the model. You sample maps. Here these are the map in the same space that your signal of interest. You can apply the forward model to go to the data space, and you can even compute statistics, which will make things easier. So you have a data space, which are just the statistics of D, okay? If you do that, everything is well written in a Bayesian model. You have parameter space, data space, and if you give me a prior, which can be completely uninformative, you can do a high-dimensional Bayesian inversion, and you can get a posterior of the model given the data. And what it means, I mean, from a conceptual point of view, is that I will try to give scattering statistics that parameterize the model. I get a map. I put it through my forward model, and I see if it matches with the data. And I can try, and I will try to get all the parameters, all the model of processes which are compatible with the data. Okay? And doing that, I can get a posterior distribution. So here, that's an example of what we can do. So actually, this example is a bit more sophisticated because we also introduce the correlation with I, but I don't want to enter in the details. Here you have the data. Here you have one of the maps that we can sample. So here it's a similar sample, but we can sample other realization. So you see it's a map which is statistically compatible with the data. And the way you can see it is that if you add another realization of the forward model, you arrive to that, which statistically you can't distinguish from that. Okay? And you can take this map and remove the signal of interest. You arrive to that, okay, which is statistically indistinguishable from a single realization of the contamination. And we also did that for the cross statistics with total intensity. You can pile up the constraint if you want and sample maps that verify this constraint. And to give you an idea, in the CMB community, at the moment, this is basically the state of the art of the estimated map from this signal. So you see that in terms of statistical properties, we probably do a bit better. And this opens a new possibilities for astrophysical observation. I mean, the framework is very general. And also here, it was a sample which was statistically compatible, but I can't guarantee you that the structures are deterministically the same, even at most scale, but the smallest one, I mean, we expect it to be correct. But we can also, as we have a model of the contamination, we can sample of the signal of interest. If we want, we can sample a lot of realization and then train a neural network to perform a deterministic recovery with error bars. And here, that's what you can have. Here, it's a deterministic reconstruction with error bars, okay? You see, it seems quite close. And we did a test with different kind of processes. And here, you can check that for each pixel, you can take data, truth, minus here we don't have the truth, obviously, but you can take truth when you have it minus deterministic reconstruction divided by the standard deviation per pixel. And you do an histogram of that, and you have something which is mean 0, STD1, which means that you have a posterior which makes what you expect for a posterior. Okay? So here it shows how we can do a successful reconstruction. And here I emphasize that no one gave us any prior model for the signal of interest, and we only had one single image. Okay? So now how can we extend it to the kind of problem here with phase separation? So in this case, it's more complicated because we have several components that we don't know. We can just write it as some kind of inverse problem. But we have a bit more data. We don't have only one single patch. So here it's Galpha H1, which are in 3 km/s bins. Okay. As I say to you at the moment, I only work with spatial structures, so we don't use any spectral information. That's something that we plan to do later on. And here it's high latitude, low, let's say, velocity component. And so doing that, we stack all these images together, and we have 36,000 patches of mixture of components. So from these patches, can we do some kind of unsupervised learning of the component and then component separation? So actually, 36,000 is a lot or not a lot, depending on what you want to do. If you want to just from scratch learn the different phases with a neural network, you will have a lot of issues because it's not a lot of images in this case, okay? But what you can do is you can say, okay, actually, there is something that I can say, and I imagine you can guess what it is, which is that these phases are well described by a scattering model. And in this case, you make everything way simpler because you already introduce a very powerful model, if you want, for the different phases. And a way to solve that we have introduced in the past is to use a variational autoencoder. So I will simplify it a lot. So for people who are familiar with it, sorry about that. So the variational autoencoder is you have an input layer and an output layer. Here it will be scattering statistics, okay? Which means that for all the data, you will put, for each of the map, the network works in a way that you put some input which are the scattering statistics and you recover something which are scattering statistics. And you have an encoder that projects the data into a lower dimensional space, dimension 32 here, and then a decoder that goes from this lower dimensional latent space to the output layer. And here what we want is the VAE, the variational autoencoder, to learn the identity on the entire dataset. Which means that on the entire dataset, if I give a map, I should have the same map as input and output. So okay, say it this way, it seems a bit trivial, but we put additional constraints, which are the fact that in the latent space, I want the encoder to project the entire dataset in a mixture of Gaussian model, okay? And I can choose the number of components. And for instance, here, as I expect to have 3 components, I can enforce the network to the encoder to transform all the input data into a mixture of 3 Gaussian, okay? And what I hope is that each of these Gaussian will correspond to each of the components of my image. And as the decoder is supposed to work for the entire dataset, then if I sample from one of the Gaussian, I expect to have a distribution of statistics for each of the components. Okay? I hope it was clear. So I can do that. And if I want, I can play a bit with the number of components to make sure I understand what is happening. And if I do that, I have a scattering model of each of the components. Okay? And if I have a scattering model of each of the components, I can perform a component separation. So to give you an idea, that's, okay, we apply that on the data. That sample, each line are different samples of the scattering model from one of the components we identified. So we said nothing to the model. We didn't say that there was one component that was noise, one that was more dense, one that more diffuse. We didn't say that. And there was an additional difficulty, which is that WNM and CNM are obviously correlated, which makes things a bit more complicated. But you see, I don't know for you, but I think that I can call this component the noise. And here I'm happy because I see that one of the components is more diffuse and the other is more dense. And typically we apply that on a simulation of the multi-phase neutral ISM, and we showed that we were able to consistently reproduce all the statistical properties of the different phases. So we have this model, and then we can apply it to component separation. So okay, you don't see it very well, and okay, it's preliminary anyway. But here on a bigger footprint, so you see 20 by 50 degrees, that's the kind of identification of Coulomb density here of the cold neutral medium, so the denser part. And we made a comparison with neural network, and from my completely biased point of view, it seems way more physical, but okay, we need to work a bit about that, on that. And as I said to you, what is nice on this work is that we were able to make this component separation only from the spatial structure. But I mean, obviously, we know that there is a lot of information on the spectral properties. We already know very well using the spectral properties to separate CNM and WNM. So it means that these are two kinds of information that we could put together to have a better modeling and separation of the different phases. Okay, so I will stop here. So scattering transform are efficient statistics inspired from neural network. So as I said, something which is very cool is that they provide a general low-dimensional parametric model of physical fields, and they can be used for different modeling and component separation tasks. And something which is very cool is that they can be applied only on a very limited amount of data. And you can also perform this component separation and inverse problem, even if you don't have a prior model of some of the components of interest. So thank you very much.
Thanks very much. We have time for a few questions.
Yeah, thanks for the talk. So I had just a naive question. So the map that you show seems quite clean, while sometimes, I mean, we have to deal with maps that are actually mosaics of different patches observed with different integration times, with different noise levels, sometimes with missing, hole, So would your method work also on this kind of heterogeneous mosaics?
I would say that if you have a good knowledge of the forward model that leads to these heterogeneous mosaics, this shouldn't be a problem. And to give you an example, the complete application that we did with the inverse problem was, for instance, here. Okay, that's a simulation from the large-scale structure of the universe, but we used the forward model, which was beam, noise, and masks, and it was able to work efficiently. Then with heterogeneous data where you can have a different resolution in different parts, you need to be able to take that properly into the posterior and communicate properly about the results. But I don't see a particular obstacle to do this kind of tasks.
This question. Your image looks like statistically homogeneous. That's what he meant, I think. The statistics looks homogeneous in your image, whereas in the data, sometimes the statistics are different. That's what.
Oh, okay. That's a good question. So there is a trade-off. So yes. So here in this example, for instance, it's very simple in terms of homogeneous properties because we see that it is homogeneous. So we won't have any problem to assume homogeneous properties. When you arrive to these kinds of data, it's already more complicated. But here we assume homogeneous properties and it wasn't a limit. Then we also try to make this component separation on full sky data from Planck mission, where you see very well the galactic disk, and you have very different properties from the high latitude and low latitude region. And there, what we did was to identify different regions on which we evaluated the constraints separately using smooth transition between the different regions. And then you have a trade-off, usual bias variance trade-off, which is how many masks you use, and the more you have, the less bias you have, the more variance you have. And I will say that in addition, for this kind of algorithm, in cases at least where the forward is homogeneous, which is not always the case, in addition, you can directly from the data do some clustering to define the region which should be treated homogeneously. So that's something which there is always a trade-off, but there is no major obstacle to do that. And we already did that in one of our projects.
Hi, very nice talk. I have a somewhat naive question, I guess. Since you mentioned source separation, if we look at extragalactic scales and we have a galaxy with multiple companions and they're overlapping, let's say, in PPV space, do you think scattering transforms can be a good way to isolate the different components in that kind of data, preserving the PPV structure. Like, because usually source separation methods that I've seen with, let's say, blind source separation with a mixing matrix, those methods are unable to recover the PPV structure completely for the individual sources. So do you think it can be an extended application of what you described?
Okay, I will need to have more information to give a more definitive answer. And we are not ready to directly this algorithm in PPV space, even if it's something that we definitely want to do. Then I would say that at some point, there always needs to be some information that you put. For instance, if you have a sum of several components that you don't know and in one single image, there is so much we can do. But then if you have a bit of information, we can start to play a bit. And I would say that what is very nice with the scattering transform is that you have extremely efficient way to characterize cross statistics, but nonlinear cross statistics, for instance, independence. If you impose independence with scattering statistics, these are extremely strong because you impose that all the scales from one process are independent from all the scales of the other process. It goes way beyond linear correlation. And usually what we can do is use ancillary data to leverage these kind of properties for component separation. For instance, here in this case, okay, if you have CMB, it can be difficult to distinguish CMB from dust, in particular where dust dominates a lot. But if you have some H1 tracer, you know that you trace the gas, you know that the gas is correlated with dust, but not with CMB. So you have an external tracer that should correlate with dust. And if you impose that CMB that you recover is independent from gas, that's a huge leverage that you can use. So in the future, what we want to do also is to leverage all these kind of ancillary data at different frequencies to help and to inform the component separations.
Okay,
but it was an indirect answer, but then I need to have more information. We can discuss.
Yeah, all right, thank you.
Yes, you're not speaking about needed computer power. Is it expensive or is it free?
I think that it's a tricky question because it's neither one of them. I would say that one of the huge advantages is that we can leverage all the libraries which are developed by the AI community and the efficient GPUs. And I would say that we are in a regime where we accelerated our algorithm by something like 1 order of magnitude per year the previous years. But nowadays, to give you an idea, on a GPU, syntheses cost something like a bit less than 1 second per map for a 256 single channel image. And nowadays, to be able to get a posterior for a 256 image with several constraints, to be able to have a posterior of sample, it's something like 20 minutes on a GPU, which is actually not that expensive, taking into account that to have one single map 5 years ago, it was 40 hours. So we are ready to scale while still keeping a single GPU utilization for several hours.